Bon dia, everyone. Well, thanks for attending and hope you find interesting this topic too as me. The talk is that I want to give is Deep Algorithm Unrolling, but in biomedical imaging applications. And like I think I would say like 3 to 4 months ago, I was asking myself this question. And that's why I got interested in this topic too. So, do we need to stop understanding the complexity of the human body and its surroundings, or we should just keep mining data? And the content of this talk will be, first I will give some context of what is a deep algorithm unrolling. We start by doing what is the model-based framework that origins the iterative algorithm, and the other approach that it's used to is data-driven approach that it's basically, or more popular these days, is deep neural networks. Then we will discuss these concepts that we use a lot in machine learning, is interpretability and generalizability. Then a bit of history of deep algorithm unrolling, and the first algorithm that was unrolled was the lista algorithm, and then how it turns into a more generic approach, what is called unrolling any iterative algorithm. Then we will discuss the applications in biomedical imaging, specifically computed tomography, and then we will discuss the effectiveness of this approach and the trends, and finally a conclusion. A model-based framework relies on a forward model that is by modeling an imaging process using physical laws. Y is the observation that we see. X is the underlying signal that we want to recover, and noise. And the function F is the mapping from image domain to the observations that we perceive. Sometimes this can be an ill-posed problem because in the nature how the imaging process is being undertaken. Sometimes we want to accelerate the acquisition and we undersample the image, or sometimes for safety reasons, in the case of CT, we use low dose of X-ray, and it's give us a very low signal-to-noise ratio. And the reliable estimation of X is, as we talk, is by capturing physical principles of manual handcrafting. And normally how the estimation of X, of the signal of interest, is by solving some optimization problem. The minimum of this function, the regularized function, and with rho is the metric of deviation of the measurements, rho is some regularization functional, and lambda is the regularization coefficient. And this problem is solved by using an iterative optimization algorithm, which is highly interpretable because we previously modeled the imaging process, or we just capture prior domain knowledge. And also alternatively to this, what we've been doing is using machine learning, which we are estimating X, learning from data, using some linear regression mapping. These regression mappings in machine learning models, the more popular ones are now the deep neural networks, because they are very powerful and they rely on abundant training, and which are learning millions of parameters through the network, and are extremely expressive, and because they can adapt towards complex patterns or complex mappings. And nowadays they are be able to use it because we have GPUs but they also tend to be difficult to interpret because generally lacks the ability of us to understand, disintegrate, and analyze and draw analogies of what is that pattern happening. And when we are going to discuss interpretability and generalizability, which are the main advantage of deep algorithm unrolling. Interpretability is defined by this author as the ability to understand sequence of operations of a trained learning system and allow us the manipulation of inner mechanisms in a principled and predictable fashion. Is key to understand concepts and also to advance the knowledge frontiers. And also it's very important nowadays in biomedical imaging because we want to ensure trust, how is the reconstruction algorithm working, and also experts, clinicians are demanding proper understanding of the region of the complex pattern of motion artifacts, and in order to predict potential failures in the model. And generalizability, I won't give the definition, but it's in the case of deep neural networks, if the data that you use for training is not abundant, then you know that it can overfit the model. But if you have the adequate training of data, then you can achieve a very high performance. And in biomedical imaging, we know that it's very time consuming and it costs collecting data from patients. So first, the deep algorithm unrolling was accidentally proposed by Gregor and Lecon in 2010. They trying to make more efficient some sparse coding algorithm. They connect their algorithm into a deep neural network. And also this work helps as an inspiration to other researchers in biomedical research and what they use in different medical imaging applications. And in this image you can see how it's first an iterative algorithm when one iteration is a function with some parameters, and then the unrolling is basically converting this iteration but in a cascade of layers, and that is equivalent to executing each iteration but with a finite number of times. Also the parameters are transferred through the network and can be trained through backpropagation, and it's because it's finite and you already have some parameters learned by the capturing the physical principles. The parameters are efficient and we don't record a lot of data. This is the algorithm, the sparse algorithm that Gregor and Lecun use. Is ISTA, was proposed by Doveshis, and which is just a linear relationship between a signal of interest and the observed quantities, and it solves also as a linear inverse problem. But just to be able to solve it, they assume that the x is sparse, so almost all are zero of the coefficients, and use W as a dictionary that is like a standard basis as a Fourier of wavelets, but also can be learned from data, which is what Gregor used. And again, they solve this minimization problem using a proximal method. In this case, ISTA is using the sub-thresholding operator with some weight in the identity matrix. But they was very slow to conversion. what Gregor wants to is to make more efficient ISTA, and then it convert to LISTA, which means learn iterative synchronous and thresholding algorithm, and which is highly efficiency learning-based method. This algorithm is a L-layer deep network and computes good approximations in a fixed amount of time. As we say, W was learned from data and integrates deep learning networks and also the domain knowledge of the iterative algorithm, which now is tailored to a specific problem and is more robust and increase the convergence speed. But they also did a bit of generalization with W. They generalized these terms into these W's, sub T and sub E, just to make it more easy to convert it into a deep learning network. This is just the example how this algorithm was as an input, a concatenated input before the thresholding. And this is the first image in the top left, was the single iteration. And then you can see how the unrolled deep network looks like repeating these iterations a finite number of times. And the train was done through backpropagation. It was a supervised training, and this is the loss function that they use optimizing the WE, WT, and lambda parameters. Where they found that the principles of LISTA could be generalized, and we not only can use ISTA as an iterative algorithm to convert it to a deep network, we can use any algorithm in this case. So they identify that we have to find first which every analytic operation per iteration that is performing in our algorithm that we want to convert, and then we can generalize these functions if necessary, and we can sometimes the proximal operators in that we use to solve the minimization problem can be used replaced by a standalone convolutional neural network or a recurrent neural network. And we can decide also if the parameters can be shared in a specific, can be shared or can be for the specific layer. But then you have to balance because that can also affect the conceptual merit of the model, but also can increase the performance. And this is how it looks like a generic unroll algorithm. We have the function and the parameters and are in each layer of the network. And this is the case of the computed tomography. We have different computed tomography techniques, and we have the model, which this technique is modeling the imaging process, and then we have in the another column the traditional approach, the iterative algorithm to solve to find the signal of interest of the image of interest, and then we have the unroll iterative algorithm that was used using this traditional approach, but with converted into a deep neural network. And then in some cases they replace, as we say, the proximal operator by a convolutional neural network. And this is the specific case of the representation of the deep gradient descent network, where the G is what was used as a CNN network, and they are optimizing the parameters of, the input of the convolutional network was the concatenation of x and the gradient that is function of the observation in the dictionary. And here you can see how effective was in increasing the signal-to-noise ratio. The first two are the two traditional approach, and this is the signal ratio that they have with this traditional approach. And the last two ones are unroll algorithms, and they have a bit higher signal-to-noise ratio, which the last one is the most successful one. This is this is the techniques that we discussed about computed tomography. And when they are comparing these techniques with a traditional approach, they can have increased the signal-to-noise ratio of over 3 decibels. And comparing with deep neural networks, it's around 1 decibel in increment, and they increase the robustness, and in the case of deep gradient descent method against perturbations. Also, they can show another type of advantage as preserving texture details of the image. And this is just overall and in other medical imaging modalities, super resolution microscopy, ultrasound, and MRI. And again, this is the deep algorithm that was unrolled. And the comparison with traditional approach and deep neural networks. And overall, the features of the parameters, and in all the features, because these algorithms that we're discussing this chapter, all of them were successful. So we always saw that there was a higher signal-to-noise ratio and more robustness, and also the metrics that they used were superior, and also and were more faster than the traditional approaches. And now we're going to discuss why this proposed algorithm, why this technique is so effective in biomedical imaging. We have to have first the linear models and iterative algorithms. We know that they generalize better, but are inadequate of fitting functions when they are complex. And in this case, they say that they have high bias and low variance. In this picture, you can see the capability of each approach to fit a function space. And in case the deep neural networks have high capacity of fit complex data patterns, and with this, they also tend to produce high dimensional parameters that require large data sets and training time, because if not, they overfit, as we mentioned. And then we have that unroll network also inherits the interpretability of the iterative algorithm. And then we have more favorable bias and variance trade-off. And also they expand a bit the capacity of the iterative algorithm. So it's between the general neural network and the iterative algorithm in the capacity of fitting the function space. But because they also integrate the domain knowledge and approximates accurately with better generalization. And then in case of biomedical imaging, they are alleviating the burden of training and requirement of large data sets. And this is some emerging unrolling trends. So the moment that people are unrolling an algorithm, they tend to use deep neural networks as a learnable operator, which is basically the substitution of the proximal operators with parameterized deep networks such as CNS and RNS. And they are not just using ISTA as initially, and they are using other alternatives as iterative algorithms. But they are also balancing the performance and efficiency trade-offs. So they are deciding if sharing the parameters to the network or being specific for the layer. And also they have to see if they make wider and deeper the networks, or but they also can be a less efficient networks. So in conclusion, we discussed the introduction of algorithm rolling, how to construct deep networks out of iterative algorithms, its application in biomedical imaging, and the effectiveness and the trends when building these unrolling algorithms. And takeaways is that if we customize the iteration algorithm, they can undermine the algorithm. And we also can have convergence guarantees that cannot be longer held. But then an approach is to extend the theory around the iterative algorithm in order to overcome that. Also can be seen as a tool to understand the power of deep networks, but also overcoming the interpretability issue about the conventional deep neural networks. And we have to keep in mind that biomedical imaging data is sometimes deficient, so algorithm running is a viable alternative in immediate training scenarios and also or with semi-supervised learning. That's all from me. Thank you.